Greetings and welcome to the study. Let's solve this problem before we start today's video. A cyclic engine exchanges heat with two reservoirs maintained at 100 degrees Celsius and 300 degrees Celsius respectively. So 100 degrees Celsius is the lower temperature and the 300 degrees Celsius is the higher temperature. The maximum work in joules that can be obtained from 1000 joules of heat extracted from the hot reservoir. That means this is QH. All right. So for a Carnot engine, neta, that is the efficiency, is equal to 1 minus TL by TH, right? So TL is given to be 100 degrees Celsius, that is 373 Kelvin, and TH is given to be 300 degrees Celsius, which is 573 Kelvin. Hence, neta becomes 0.349. All right. Now we know that neta is equal to output work from the input from the engine upon the heat input from the hot reservoir, right? So since QH is given to be 1000, therefore W comes as 1000 into 0.349, that is 349 joules. Hence, A part is the correct option. Now we move on to a very important thermodynamic variable, that is entropy. All right. So before we come to entropy, let's go on and understand the second law of thermodynamics. So second law, as we already discussed, it deals with dissipation of energy. So it says that all the heat cannot be converted to work. Some of it has to be dissipated as well, right? That's what is given by the second law, right? So second law also gives us the direction of change of a process. All right. It states that all the spontaneous processes are to some extent irreversible and are accompanied by a degradation of energy. It also means that it is impossible for any self-acting machine to transfer energy from a given state to a higher state of availability. So if suppose we if we take a particular machine that is at state A, all right, that is currently at state A, and you want it to transfer energy to state B, which is at higher energy state. So it is not possible that this process takes place simultaneously, spontaneously. That's not possible, right? It's not possible that this process would take place spontaneously. Okay, so any self-acting machine cannot transfer energy from a given state to a higher state of availability. All right, that is the second law. So a lot of basic phenomena can be satisfied according to the first law, but they are not physically possible. For instance, let's say that the water is flowing at a speed of 200 meter per second and it is brought to rest. So this is the initial velocity and this is the final velocity, that is 0. All right. So the change in kinetic energy per unit mass is given to be half delta V square, which comes as minus 20 kilojoules per kg, right? And by energy balance, we know that change in kinetic energy, potential energy, and enthalpy is going to be equal to 0 because there is no heat added or extracted and there is no work added or extracted. So altogether, this change is going to be 0, right? Hence, since we've taken change in potential energy as 0, we have not taken any height difference. Therefore, we finally get enthalpy change plus kinetic energy change is equal to 0, which gives us the change in enthalpy as 20 kilojoules per kg. All right. This is what we get, that if we reduce the velocity from 200 to 0, then in that case, the enthalpy change would be 20 kilojoules per kg, which is fine. All right. So if we reduce the velocity of 20, if we reduce the velocity by 20 from 200 to 0, then the enthalpy would increase by 20 kilojoules per kg. Okay. Now, if we do the reverse, that is, if we supply heat equivalent to 20 kilojoules per kg, will it be able to raise the velocity of water to 200 meter per second? No, that's not really possible, right? If that would have been possible, then, you know, while we heat, uh, while we heat fluids, or while we heat water, let's say, while we heat water on a gas, then it would have started flowing. That's not really possible. So energy balance alone cannot explain this phenomena. We need the second law to explain this phenomenon. Okay. So to understand the directional behavior of a change, we need to understand spontaneity. All right. A change is brought due to some driving force. If a body falls from the top, it is due to the gravitational force acting as a driving force. Okay. So suppose there is a body and it is falling from a height of h, then that body actually has a potential energy which is mgh. And this potential energy is due to the gravitational force. So gravitational force is basically the driving force in this case. It is pulling the body towards the earth, right? So if current moves from one point to another, it is due to the potential difference acting as the driving force. Now, if the driving force is applied without the application of any other sources, the change is spontaneous. Okay, so any source, if there is no source that is uh, used for application of driving force, then in that case, the change is known to be spontaneous. For example, if you talk about this ball, all right, so this ball, if you leave it without acting any force, any external force on it, without doing anything, if you just leave it, it will automatically fall. All right. That is a spontaneous change. That is a spontaneous change. All right. However, if a ball is on the ground itself, if a ball is on the ground and you leave it, then will it reach the top? No, it won't reach the top. You will need to push it. All right. You will have to push it. So there's some external driving force from your side that is required. Therefore, this change, that is moving from this state to this state, it is non-spontaneous in nature. All right. This is non-spontaneous. It will not happen on its own. All right. It'll not happen on its own. Okay. So yeah, I have given the same example over here. Now let's say we want to throw the same ball at the top. We would need to apply some additional force to make that possible. Thus, the change is non-spontaneous in nature. Okay. If change is spontaneous, then we are sending the system from a higher energy state to a lower energy state. So the ball is dropped from the top, it goes to the bottom, which is a lower energy state. Okay, so energy at the top is mgh, while energy at the bottom is going to be 0, right? In order to quantitatively analyze the spontaneity, we need physical quantities, which increases or decreases based on the spontaneity of the process. This physical quantity is defined as entropy. All right, this physical quantity, we define it as entropy. Entropy is denoted by the symbol S. Okay. So physically, it is defined as the degree of randomness. The more random a system is, the more would its entropy be. This quantity helps in explaining the spontaneous nature of a process. All right. So for example, let's take this particular system. Over here, you can see this is a container which is divided into two chambers. All right. One chamber contains gas molecules. Okay, it is filled with gas, while the other chamber is empty. Okay, the other chamber is empty. If the separation between the two chambers is removed, where would the molecules actually move? We can all answer that these molecules would move towards chamber 2. Now, this is our common sense that we have seen that this actually happens. But how can we explain this happening? Why is it actually happening? The molecules would obviously move towards the empty chamber. So we are going to explain this now through entropy, right? As the molecules move from the crowded chamber, that is chamber 1, to the empty chamber, that is chamber 2, they get more space to move around. All right. Hence, they are able to spread easily and their distribution is more random than before. Now, as you can see over here, the distribution is less random. Over here, the distribution is more random. All right. So the more is the more random the distribution is, the more is the entropy. All right. The more is the entropy. Thus, in general, keep this in mind that there is an increase in entropy when the change is spontaneous in nature. All right, mathematically, this is written as delta S is greater than 0 for a spontaneous change. All right, for a spontaneous change. For a non-spontaneous change, delta S is negative. All right, for a non-spontaneous change, delta S is negative. All right. For example, when we talk about ice, okay. So when we talk about ice, so ice, if you keep it at room temperature, what will happen? It will automatically melt and form water. All right. The reason behind this is that ice is less random in nature and water molecules, since they are more spread, therefore they are more random in nature. So entropy of ice is lesser than entropy of water. Hence, overall, there would be an increase in entropy, which makes this process spontaneous in nature. All right. Mathematically, entropy is defined as the heat energy per unit temperature that is unavailable for doing work. Okay. So delta S, or in differential terms, we'll say ds is equal to dqr by t. This r, the subscript r, it actually means reversible. All right. This rule is applicable for reversible process. All right. For an irreversible process, ds is generally greater than dqr by t. Okay. Hence, entropy change for a system, for a reversible process, it is given by delta S, which is integral of this term from T1, that is the initial temperature, to T2, that is final temperature. Okay. So now let's deal with entropy calculations. Okay. So we know that ds is equal to dqr by T. Correct. Now dq by first law of thermodynamics, we can have dqr is equal to du plus dw by T. Right? du plus dw by T. du is nothing but cv dt, right? And dw is nothing but pdv, and this whole thing by T, that is ds. All right. So we'll have ds is equal to cv dt by T plus pdv by T. Correct? So now when we integrate this, so integral of this is quite easy. Cv ln T2 by T1. That is fine. And P by T, when we use the ideal gas equation, so we have PV is equal to RT. Hence, we'll get P by T is equal to R by V. Hence, this becomes plus R ln V2 by V1. All right. This is one very important equation for entropy. Delta S is equal to Cv ln T2 by T1 plus R ln V2 by V1. Okay. Then we also know that Cv, since we know that Cp minus Cv is equal to R, hence we can write Cv is equal to Cp minus R. So in the previous equation, in place of Cp, we can write, in place of Cv, we can write Cp minus R ln T2 by T1 plus R ln V2 by V1. Correct? So this can be written as Cp ln T2 by T1 plus R ln V2 by T2 into T1 by V1. correct? Then Cp ln T2 by T1. Now from equation of state, general equation of state, we have T1 V1 by T1 is equal to T2 V2 by T2. Hence, we'll have V1 by T1 into T2 by V2 is equal to P2 by P1. So this term can be written as, this term can be written as P1 by P2. So plus R ln P1 by P2, which can be written as minus R ln P2 by P1. So you can actually use both. If you know the initial pressure, initial temperature, final pressure, final temperature, then you can use this equation. If you have initial temperature and volume and final temperature and volume, then you can use this equation. All right. So now let's generalize. This was our generalized calculation for entropy. Let's go to more specific conditions. So for example, let's go for an isothermal process. So for an isothermal process, we have T is equal to constant. So T1 would be equal to T2. So in that case, your delta S can be written as CV, sorry, your delta S can be written as R ln V2 by V1, which can be written as R ln P1 by P2. So we've used both the equations of entropy, the first one as well as the second one, to get this result. Okay, so this is for an isothermal process. Then if it is an isobaric process, so we are going to use the second equation. So we get delta S. Isobaric means constant pressure. So delta S would be Cp ln T2 by T1. Okay. Then if we move on to an isochoric process, that is a constant volume process, then in that case, you have the first equation. So delta S would be equal to Cv ln T2 by T1. Okay. Then the fourth process can be an adiabatic process. So for an adiabatic process, you know that dq is equal to 0, right? Therefore, ds, which is dq by t, is also going to be equal to 0. Hence, usually adiabatic process, a reversible adiabatic process, can also be termed as isentropic process. Isentropic process. So it is termed as an isentropic process because when the heat, when a reversible adiabatic process takes place, then in that case, dq is equal to 0, and therefore even ds would become equal to 0. Okay. And finally, we have fifth one, which is isothermal mixing. Okay. Isothermal mixing. So when isothermal mixing takes place, then in that case, you usually have, let's say you have a big container with two chambers, chamber 1 and chamber 2. Chamber 1 contains gas A with pressure P1 and temperature, let's say T. And the second chamber contains gas B, pressure P2 and same temperature T. So when this separation is removed, then in that case, these two gases, they are going to be mixed. And since the temperature is same, therefore they are going to be mixed isothermally, right? They are going to be mixed isothermally. So in that case, the change in entropy is given as minus R sigma yi ln yi, where yi is the mole fraction of ith component. All right, yi is the mole fraction of ith component. For example, over here we took isothermal mixing of A and B. So let's say Na moles of A are initially present here and Nb moles of B are present over here. So in that case, Ya, when they are mixed, Y is going to be moles of A upon total moles, and Yb is going to be moles of B upon total moles, right? So we are going to have delta S is equal to minus R Ya ln Ya plus Yb ln Yb. Okay, so this is the formula for entropy. Okay, so these are the generalized, these are the process specific entropy changes. So for an isothermal process, isobaric process, isoporic process, adiabatic process, and isothermal mixing process, these formulas can be used. But you actually don't really need to remember all these equations. Only two major equations that you need to keep in mind are these. Equation number one, delta S is equal to Cv ln T2 by T1 plus R ln V2 by V1. And equation number two, that is Cp ln T2 by T1 minus R ln P2 by P2. All right.